Tipste olanlar ses geliyor mu?
Geliyor hocam.
Peki. Hello everyone, today we will be talking about semaphores. We will continue our journey with the synchronization problem. Now last week we talked about semaphores superficially. We made an introduction to the topic. I know that we have already seen these concepts in the context of the operating systems course. So here our priority will be to get a better grasp on how to use semaphores in order to solve basic and intermediate synchronization problems. For more advanced synchronization problems, we will have to use monitors and condition variables probably in a couple of weeks. So today we will take a look at some classic synchronization problems along with the System 5 semaphores. And at this point, let me underline that System 5 semaphores are not allowed for your midterm. Don't use System 5 semaphores in your midterm. Only POSIX semaphores if you need them. Okay? So, any questions before we start related to the course? Yes, please. Bugün alınmayacak. Gelecek hafta alınacak. So next week too, also we will be in this classroom until the end of the semester, hopefully. I have missed you. But of course, it is not mandatory to be present here. If you want to continue to follow the course online from Teams, no problem. Yes, both lectures. Right now I'm recording the session. Any other questions? Okay. Now class, here we have a classic example. We have a stack. This stack is a standard stack, a standard data structure containing some integers. It is a shared array T containing the values from 1 all the way to 5. So the bottom of the stack is 1, and at the top we have the value of 5. And S is simply an indicator of the next position, or rather the top position of the stack. So in this case, 0, 1, 2, 3, 4, it points to the top of the stack. And we have two processes, two very simple processes. One of them is trying to execute the push function, and the other one is trying to execute the pop function. Both of them are operating on the same stack. Now maybe this stack is, it takes place in a shared memory segment, so both processes can access it. So what happens? Possibly, not necessarily, but possibly, process 1 might start to push 6, so it will first increment the position of S. So from 4, it will become 5. So the next position where it is supposed to insert the value 6. And at this point, a context switch might take place. Now, what was a context switch?
Change flow of program to another process.
Exactly. So a context switch can take place. So instead of now executing process 1, we freeze it in memory and we continue to execute process 2. Now process 2 will try to pop, but process 1 didn't yet finish pushing. So in this case, it will execute the first statement of the pop function, and it will try to pop the top element at the position S. But unfortunately, S is not 4, it is 5. So it is pointing to what? 0, 1, 2, 3, 4, 5. It is pointing to some random value beyond the value 5. So it will pop, who knows what, a random value. And then it will decrement S. So S from 5, once again, will become 4. It will return that random value, return V, and afterwards, since process 2 has finished executing, process 1 will get a chance to continue. Now, S is right now 4, so it will place the value to be pushed, 6, into the 4th position. So it will overwrite the value 5 in that stack. So what is the result of this? Stack gitti. It is a corrupted data structure. We lost it. The bottom line of this entire synchronization session, of all of these sessions basically, that we have been going on since the previous week, is that there is no way of guessing, there is no way of setting when which process is going to be executed, when which process will be switched with another process. That is completely up to the kernel, 100%. You cannot modify it, you cannot postpone it, you cannot cancel it. If the kernel wants to interrupt your process in order to continue another process, it will do it. And according to the law of Murphy, it will do it at the worst possible moment for your process. So if there is a chance for your project, for your program to fail, to crash due to a missing synchronization measure in your project, it will take place, very probably. Now, a critical section, as we have already seen in the operating system course, is simply a block of code that is using a shared resource, a resource that is shared across multiple processes, such as a stack in this particular example. And the only thing as developers that we have at our disposal in order to solve these synchronization issues is basically to make sure that at any given moment, only one process or thread can take place and execute inside the critical section. That's the only thing that we have at our disposal in order to solve synchronization problems. And that's what we will be striving for, using semaphores, using mutexes, using condition variables, using monitors. That's the only thing that we can do. And fortunately for us, it is sufficient in order to solve these problems. This way, even if the kernel does its best in order to ruin your projects by suspicious context switch at the most unfortunate moments, it will still fail. So your programs will successfully complete. The kernel will be unable to hurt you. So Kayıl, sen kimsin? Niye geç kaldın ya? Birazcık. Tamam, hadi geç bakalım. Gelecek hafta almayacağım. So how can we solve this simple program using a semaphore? Well, very simply, all you have to do is, the general principle with semaphores is to surround the critical section. So maybe it's one instruction, maybe it's two, maybe it's 10, maybe it's 20, 50, maybe multiple function calls. If it is a critical section, meaning that if you want only one process to be executing inside that critical section at any given moment, all you have to do is surround it with a wait and post. The important point at this note is that all the processes, P1, P2, P3, all the way to N, that you want to synchronize with respect to this critical section, they must be using the same semaphore. So if it is M for P1, it must also be M for P2. They cannot be synchronizing on distinct semaphores. A semaphore that can acquire only two values, 0 and 1, is called a binary semaphore. Students often confuse them with mutexes. A mutex and a binary semaphore are not the same thing. I mentioned the difference in the previous week. So let me repeat that since it wasn't clear. The difference between a mutex and a binary semaphore is that when you lock a semaphore, and by lock I mean call wait, such as in the case of P1. Now in that case, can process P2 unlock the semaphore by calling post? Of course. Can you do the same thing with a mutex? No. Whoever locked the mutex, that's the thread that can only unlock it. When I was a student, my professor used the analogy of a toilet. So whoever is inside and has locked the door, that's the one who can unlock it. Now class, you will encounter many types of synchronization problems in your professional careers. If you're lucky, you won't encounter too many of them. But those that you will encounter will very probably be in their majority relevant, related somehow to the producer-consumer paradigm. This is by far the most frequently encountered synchronization model out there. The main idea is that we have two groups of processes or threads, and one of these one of these groups of processes or threads, for now let's forget threads, one of these groups of processes, they are producing something. Maybe they're producing numbers. Geç kaldın. Gelecek hafta almayacağım. One of these groups of processes are producers, so they're producing something. They're producing numbers, database connections, they're producing sockets, they're producing matrices, they're producing who knows what. And the other group are the consumers, and the consumers are consuming them. They are removing these pieces of data from one or more data structures or databases. Now, if you have an unbounded buffer case, meaning that you have an infinite buffer, you have an infinite storage area in order to store those products that the producer is producing and the consumer is consuming. Well, in that case, what is the synchronization issue that you might encounter? Well, the consumer process must execute only if there is something to consume in the buffer. So if the array, the data structure, the database is empty, the consumer must wait until there is something to consume. Well, that is very easy to solve. You can use a semaphore named full, for example, initialized to 0. Why 0? Because initially you have no products, 0 products. And if the consumer starts working, starts executing by calling wait full, and since full is 0, no products, what will the wait do? It will block the process. Until when? Until the value of the semaphore is greater than 0, in which case it will decrease it by 1 and continue after wait. And what is the producer doing in the meantime? Well, the producer simply in an infinite loop, once again, it just keeps on adding products into the database, the buffer, array, graph, database, whatever you call it, into the storage area. And after every product, it is posting full, meaning that there is one more product. So if there is, the producer doesn't know, if there is a consumer process waiting for a product stuck at this wait, it will have a chance to continue. Questions? Ya hocam bunlarla gelmeyin bize diyorsunuz ya. Bu nedir ki bunlar ya? Sabah sabah bunun için mi geldik? Biraz daha zor yok mu şunu? Yavaş yavaş. Buyurun. Yes, we do need another semaphore, but we're going step by step. And this is the next step. Now, where is it? Ah, here it is. Before getting to the empty semaphore, we still need something different. And that problem is that the reason why we need it is that we are not protecting the storage area. So we still need to lock the storage area. Why? Because if we do not surround the production of the products and the consumption of the products, so the add and take functions, that means while, for example, the producer process or one of the producer processes is inside the buffer adding something into the data structure, there might be a context switch. A consumer process might get a chance to execute, enter the same data structure, and ruin it, just like with the stack. Or maybe it was a database. Before the other process got a chance to complete its writing into the database, another process came in trying to read the database. That shouldn't happen. So what do I have to do? I have to surround the critical section with a wait and post. Of course, all the producers and consumers are going to use the same lock, so that at any given moment, only at most one process will be inside that critical section, either in add or inside the take function. So this way it is guaranteed that at any given moment in the storage area, inside it, there will be only at most one process. So that's why we have this lock semaphore initialized with a 1. Why 1? Because initially the storage area is unlocked. So as your colleague has mentioned, we have solved the underflow problem in the sense that there must be at least one product for the consumer to continue. But what about the overflow problem? So what happens if the producer tries to produce, but the storage is not infinite and it is already full? Well, in that case, of course, theoretically speaking, this part is very easy. All we have to do in this case, add one more semaphore, empty, representing the empty locations. Now, this is an important point at this note right here, because the meaning of the semaphore is completely up to us. So if you have a semaphore with a value of 56, what does that 56 mean? It depends on you. You decide what that 56 will mean. In the case of full, it represents the number of products. In the case of empty, it represents the empty spaces in your storage area. So it is completely up to us to decide the meaning of the numbers represented by the semaphores. And this finally is the complete form of the bounded producer-consumer paradigm, at least in pseudocode. And at any given moment, of course, empty plus full will be at most equal to n. Any questions about the producer-consumer before we continue? Okay, class. Now at this point, please pay attention that the order of these instructions, of these statements, is also very important, because if you make the mistake of, instead of using first a wait on empty and then locking the storage area, and instead of that you interchange, you switch those statements, the entire system breaks down. Why? Because the producer will get the lock, and if there is no empty space to produce, it will wait for an empty space, but it still keeps the lock. So that means it will be waiting for a consumer to consume something so that there will be an empty space, but it is keeping the lock due to the wait M, in which case no consumer will get a chance to enter the storage area to consume something, which means the producer will wait indefinitely. Any questions? By placing the statements in the correct order. Class, when it comes to synchronization, it's very tricky. There is no step-by-step instruction book on solving this stuff. You encounter a problem, you analyze it, you try to figure out beforehand, what are the synchronization risks that I'm facing here? What can go wrong? You try to see that, you try to visualize that. Once you visualize those risks, then you start developing a solution towards it. That part is difficult. But what is even harder than that is that, let's say that you missed one of those risks. You saw that, yes, there is a critical section, I need to surround it with a semaphore. You saw that there is an underflow problem, but you forgot about the overflow problem. You develop your solution, you test it, it's working. You test it twice, to be sure. You test it 10 times, to be sure. You test it on 2 different machines, to be sure, and it's working. But there is no guarantee that during those 20, 30, 50 tests, that the overflow problem is going to happen, that is going to take place. And of course, the day will come that you will have to conduct a demo. The day will come that you will have to present your project to your client, to your boss, and it will fail, very probably, due to an overflow problem. So what can you do in this case? Well, not much, really. You have to do your best while thinking about those risks in order to figure out what can go wrong. And that, of course, requires experience, and it requires a very strong grasp of how exactly those processes will interact. And that is why they pay a lot of money to the people that can actually deploy these systems without risks. Yeah. Next part. Let's make these things a bit more interesting. Now, when either of the producer or consumer only requires just one resource, it's very easy to solve it. I mean, you've seen the solution, you've seen it in operating systems, it's very easy. But what happens when a process requires multiple resources? So let's say that process P1 requires 3 resources in order to continue some calculation, computation, whatever, and process 2 requires 2 resources. And initially, we only have 2 resources, which means P2 can execute because it only requires 2. And P1, which requires 3, should be waiting. Now, if you make the rookie mistake of executing 3 wait statements, since each of them will only decrease the semaphore by 1, well, in that case, this will very probably fail. Why? Because very simply, after the first wait might be executed, just might, be executed by process 1, which means that S was 2, it will become 1, and at that point, there might be a context switch. P2 might get a chance to execute. It will execute the first wait, so S was 1, it will become 0. It will try to execute the second wait, but since S is already 0, it will be blocked. After a while, the kernel will see that, well, P2 is blocked, but of course the CPU must never be idle, so it will try to figure out something else to execute. It will execute Firefox, it will execute Google Chrome, it will execute who knows what, and eventually it will try to execute P1. And it will see that P1, which will try to execute this wait, well, it will also be blocked because S is still 0 for everyone. And as a result, even though S was 2, so P2 could have executed by taking 2 pieces of resources. Instead, one was allocated to P1 and another was allocated to P2. And now nobody can execute, the system is locked forever. Instead, what we needed, was an atomic, indivisible, linear, an atomic wait statement that could decrease the value of the semaphore by k being at least 1 or 2 or 3. That would have been very nice. That would have solved this problem immediately. So you could use wait S3, so atomic decrementation of S by 3. So that means if you call this wait right here, it will try to decrement S by 3. If the value of S is at least 3, it will decrement it by 3 and it will continue. But if the value of S is less than 3, it will be blocked. So it's all or nothing, either 3 or it blocks. There is no partial decrementation in this case. And of course, the same thing is valid for wait S2. And that's exactly what we could have used in order to solve this. It is not necessary, but it is sufficient. This functionality, this behavior is provided by System 5 semaphores. POSIX semaphores, they cannot do it, at least not directly. And you only have POSIX semaphores to work with for now. Orada hiç arka tarafa bakmıyoruz. Milletin sorusu var mı yok mu hiç? Neyse. Soru varsa herhalde ses çıkarırlar. What is the System 5? Why System 5? Why not System 4? Why not System 6? Well, System 5 is basically one of the versions, one of the important versions of Unix that appeared when I was one year old, long time ago. And up until 2 years ago, there were 3 variants. There are still 3 variants that are based on System 5, commercial variants. Basically, System 5 is another standard, another widely encountered standard, a protocol for operating systems besides POSIX. But it is not as widely acclaimed as POSIX. Now, Linux has support in general for the System 5 tools. In System 5, as a protocol, it is basically, how should I put this? It is part of the single Unix specification, which is in a way an extended POSIX. But you cannot really trust it for in terms of portability. So in general, if your priority is to develop a highly portable application, well, in that case, I recommend avoiding System 5 tools. Unless, of course, you are certain that your program, the product that you're going to develop, will only be deployed on systems that definitely support System 5, in which case, feel free to use them. That's completely up to you. Now, there are certified systems in terms of SUS, which is the larger POSIX extended standard. You can see the list right here, and it is quite limited. Now, Linux is mostly compliant, which means that it is missing many, who knows how many, elements of the standard. So do not rely on their portability across Linux systems. And if you ask why more operating systems don't get certified, well, that's because it is very expensive. And so only large companies like Hewlett-Packard, IBM, Apple, etc., they can afford to get this certification. Now, let's say that we want to use System 5 semaphores. How do you manipulate semaphores in such a way that you can atomically decrement by multiple values a semaphore? And not only that, with System 5 semaphores, you can atomically decrement multiple semaphores. So you have 16 semaphores, and you want to wait for all of them atomically. So either wait will succeed for all 16 semaphores, or if it is unsuccessful for even one of them, it will block completely. Ya hepsini indirecek birer değer, ya hiçbirini. 16 tane farklı semaforla. Is that possible with System 5? Yes, it is. You can do that. In fact, even with more semaphores than 16. That's how strong it is. That's how powerful it is. Atomic decrementation by multiple values and also atomic decrementation of multiple semaphores. It's quite general. And not only that, but it also supports additional operations, such as the zero operation, which is not available for POSIX. Let's take it step by step. What are the general steps when using System 5 semaphores? Well, you first create them or open an existing semaphore by using the semget system call. You use semcontrol or semctl in order to initialize those values. Of course, if you have multiple semaphores, you need to provide multiple initialization values. After they have been initialized, you're ready to use them. You can perform wait, post, zero, whatever you want by using the semop system call. And once you are done with all of them, all you have to do is just remove them from the system so that they will be no longer available to any other process by calling once again semctl and giving it the flag of IPC RMID. So remove those processes. This is the general flow. The semget system call. 3 parameters. It returns the semaphore set identifier. Now, semaphore set identifier. We are not talking about a single semaphore, not necessarily. We are talking about a set of semaphores. And of course, in case of failure, -1, and setting the error with the corresponding value. Now, the key is supposed to be a unique identifier. So it's basically like a name, just like in the case of shared memory. So if you don't want to give it a name and you want to use something random, you can simply just use the constant IPC private. Nsems, the number of semaphores in the set. So how many semaphores are you going to manipulate atomically? 1, 2, 16, 32, 512. That's the second parameter. And of course, semflag, well, that is simply just the file permissions. So these semaphores will be accessible by which users, by which group, etc., etc. Now, semctl, now this is a bit stronger, and it is a bit, well, relatively speaking, it might get a bit complicated if you really push it to the limits. semctl is there for 2 reasons. 1, initialize the semaphores that you have just created with semget. 2, in order to remove those semaphores from the system. That is the most frequent purpose of semctl. Now, semid is of course the identifier of the semaphore set that has been just returned by semget. Semnum is the identity, the number, the index starting from 0 of the semaphore upon which you want to operate. So for instance, I want to initialize semaphore number 2. So that's the index at position 2. And of course, CMD, the command is, what do you want to do with that semaphore? Do you want to remove it? Do you want to initialize it? Do you want to get some other information about that semaphore? No, not other information. What else can I do with it? You can do a lot of stuff with semctl. Now, semctl allows you to access who owns, what are the permissions of that semaphore, when was the last operation that took place on the semaphore, the date and time, creation time, and last modification, how many semaphores are in the set. These are all pieces of information that you can access actually by using semctl. Not that you will need it, but very probably you won't, but still, semctl is not simply for initialization and removal. It can provide some valuable pieces of information. Yes?
Solve all synchronization problems using 5 semaphores or?
No. No. In generally speaking, you cannot solve all possible synchronization problems with semaphores. There is only one tool that is theoretically guaranteed to solve any synchronization problem that you can think of, and those are, yes, monitors. So what's a monitor? It's basically condition variable plus a mutex together. So they are guaranteed that they can solve it. If you cannot solve it, you encounter a synchronization problem. And if you cannot solve it with monitors, then it's your problem. It's not the fault of the monitors. They can solve it. You have to just think harder. But with semaphores, it is possible that sometimes you simply just, well, it's too complicated for them because semaphores are simply there for counting. So example, I want a process to wait until a certain file has been downloaded at 85%. How do you solve that with semaphore? we will talk about that in a few weeks. So what about this union here? Now this is the tricky part with SEMCTL. Now as you can see here, it has three parameters. So SEMID, SEMNUM, and CMD. And there is a fourth optional parameter. Hocam optional mu ne oluyor burada? Şurada gördüğünüz gibi. It can admit optional parameters, in fact multiple of them. And that optional parameter is supposed to be of the type union SEMUM. Now, of course, you might say, ya hocam unionları biz zaten gördük ya, yani we've already seen that during our first year. And we know C. But the tricky part here is that this union has to be defined by your program. It is not defined anywhere. You will not find it in a header file, somewhere in Linux or wherever. You have to define it if you need it. Hocam niye böyle bir şey var ya? Why do I have to define it? I mean, couldn't they just, couldn't they bother to include it in the header files? The answer to that question is a bit complicated. I will not get into that. You can look it up online, but please remember that if you intend to use Union SEMUM in order to exploit the advanced aspects of SEMCTL, you have to define it on your own. And what does it contain? Well, it can contain int var, distract. So this is the place where you will store the semaphore values during initialization. You will very probably never use this fourth field. So if you want to initialize multiple semaphore values at the same time, you will be using this third field with the array and so on. What are the additional information pieces that you can obtain by using this struct SEMID-DS, struct semaphore identity data structure? You can get the process ID of the process that last modified the semaphore. It is accessible through this struct. The number of processes waiting for the semaphore, time of last change, time of last operation, and so on. So a lot of statistical information, which might or might not be useful for your project. Example, how do you initialize a binary semaphore? You create a union SEMUM argument. Here we have the identity, the index of the semaphore that we want to initialize. Here we have an array of size 1. We initialize it to 1, so we want the semaphore to have the value of 1 initially. We place the pointer inside the union, and we simply call SEMCTL with these 4 arguments. So I want to operate on this semaphore, represented by SEMID, this semaphore set. Inside this semaphore set, I want to set the value of all the semaphores. Hocam, if I say set all, then what is the meaning of the second parameter, which was supposed to represent the index of the semaphore? It is ignored. If you use set all or get all, well, in that case, you don't need an index. That means it is going to operate on all the semaphores of the set. And how is it going to set them? By using all the array values inside the union argument. That's it. Questions? So let's say that you have initialized them. Then how do you actually conduct a wait and post with system 5 semaphores? Well, the main and only system call that you have available is semop. The first parameter is, of course, the identity of the semaphore set as returned by semget. The second parameter, semboof, this one will represent the actual array containing the operations. And of course, nsops represents simply the size of sops. Now, what is inside this semboof? Inside it, we have an unsigned short representing the semaphore number upon which this operation will be applied, starting from 0. We have the operation to be conducted, a wait, a post, something else, represented simply by an integer, and just a flag, which is generally not used. Examples? What happens if semop is greater than 0? Well, that means, for instance, if it is 5, this is a post operation, but it will add 5 to those semaphores. If it is negative, strictly negative, then that means this is a wait operation. It will decrement that value from the semaphore. And what happens if it is 0? Now, this is an operation that is not available in POSIX. That means it will block the semaphore until its value becomes 0. If you call semop with 0, that means this is a new operation blocking the semaphore until it is 0. So if it is 5 or 6, etc., it blocks, and it only continues, the process will only continue when the semaphore becomes 0. This is a new one. An important part. What happens if the process receives a signal while it is blocked, while it is conducting one of these SEMOP operations, maybe a post or whatever? The SEMOP is interrupted. It is interrupted, it is cancelled, error is set to interrupt, there was an interruption, and it is not automatically restarted. So that means if you want to reliably, robustly execute a wait or a post with the System 5 semaphores, you have to use that macro thing that we saw during our second week. Remember that? We had a macro, a while loop, where we repeatedly called read, write, as long as it was interrupted by a signal. And we kept on repeating it up until it was either successful or there was an error other than a signal interruption. So that's the way that you're supposed to use this stuff if you really want it to be robust. Otherwise, you spend all that time designing your synchronization solution, semaphore there, semaphore here, semops and unions and so on, and a signal arrives and it ruins everything. These things happen. And they usually happen during demos. A problem with System 5 semaphores. I mean, if they are so great, why isn't everyone using them? Creation and initialization with System 5 semaphores are two separate steps. The creation and initialization are two separate steps. This is causing a problem. Why is the problem? Imagine that we have two processes. One process is creating the semaphore, obviously, and it's trying to also initialize them. So what happens when another process tries to use the semaphores before they have been initialized? How does the other process know that they have been initialized? Maybe the kernel will interrupt the first process and insist on executing the other process, which will try to use those semaphores even though they haven't yet been initialized. Get the program. Super. How do we avoid this? Solution number one. Ensure that a single process is in charge of creating and initializing the semaphore, so nobody else is touching it somehow. Make sure that there is only one single process. Nobody is trying to initialize it in any way. That process will be in charge of creating it, initializing it, and maybe, very probably, it will be this process that will create the other processes after it is done. Well, that's a classic way of solving it. But another technique for which there is a complete example, tam bir örnek var böyle kocaman, there is a complete example in your textbook for the second case. This is a very delicate trick. And the trick is that there is a field, sem o time, inside the struct semid, ds, which contains, of course, the time of creation, or rather the time of last change. It's a timestamp. And so another process can check that timestamp, and if it is 0, that means nobody has used it yet. So the process that is responsible for creating and initializing those semaphores can create them, initialize them, and whenever it is ready to open them for use to the other process, it can very simply just conduct a simple operation, a NOP, without modifying actually the value of the semaphore, so that the timestamp will be updated and it will be something other than 0. So this will be a signal, basically, a signal to the other processes that the semaphore is ready for use. There is a full example on this in your textbook. What are the limits on System 5 semaphores? For instance, on my machine, if I use the command IPCS, I see that the maximum semaphores that I can have per array, so in a single set, is 32,000. So I can theoretically conduct an atomic operation on 32,000 semaphores. System-wide, so all processes, all projects running concurrently in the entire kernel, supports quite a large number, as you can see. I think it's what, a billion, something, who knows. The maximum ops, maximum different operations per semop call, so how many atomically collected multiple operations you can fit inside a single semop system call, that's 500. Long story short, the API is a bit complex when compared with POSIX semaphores. there is a problem with the initialization part, so you need to pay attention to that. You have to take care of the keys and so on. But on the other hand, it provides you sets of semaphores, which makes it extremely easy to solve most of the synchronization problems that you encounter, if not all of them. No, not all of them, of course. Yes?
You can use macro every previous for writing operation.
Yes.
We have to use, or we can use for semaphores, for example, wait or pause. We have to do in topic semaphores too, or it's just simplified semaphores. And
Well, for that, you will have to check the man page of POSIX semaphores in order to see what happens when you receive a signal while you're waiting. So if you want your program to be truly robust, you will have to take a precaution against that. Now, I will not push it that far. I will not send signals to your processes while they are waiting. I will not do that. I will not try to ruin your programs that hard. I'm just telling you that in the future, if you really want your programs to be robust and you're using these operations, you have to invoke them repeatedly inside a while loop, just like the read and write system calls, so that they will be robust against signal interruptions. And if I wanted to ruin your projects and that part was missing, I would simply have to just send the signal while it was waiting in order to wake it up while the condition has not yet been satisfied. But I will not do that, of course. Evet. Like Now, I'm guessing that you have already done this example, of course, in the operating systems course. Yes? Yes? No? Yes? And how far did you go in those solutions from a practical point of view? So your project gave you the pseudocode, obviously, and was that it? Did you go any further than that? So you used just semaphores in order to solve it? Anything else? You solved it with semaphores, right? Okay. And besides the dining philosophers, what other examples did you do? Classic examples such as this one with the name, böyle isimli örnekler başka gördünüz mü arkadaşlar? Psikolojide. İsmini söylemediniz. There was another one. What? The reader-writer problem. Güzel. Ona da biz de bakacağız ama biz daha farklı bir açıdan bakacağız. We will look at those problems now from a more practical point of view. Now, the context, of course, is familiar to you. We have these 5 philosophers that are trying to dine, and each of them has a fork to the left or right. So 5 philosophers with 5 forks. The forks are the resources, and every philosopher requires exactly 2 of those resources. Not 1, not 3, exactly 2, and not just any 2, but the one to his or her left and right. Now, obviously, these philosophers are supposed to be doing some thinking. Now, the thinking is the non-critical section, so they can think whenever they want to. But eating, that's a critical section. Why? Because while eating, you are using shared resources. So that means we have to protect the use of those forks. Now, of course, at this point, you might ask, who eats using 2 forks? That's a very good question. That's a very good question. Because initially, this problem wasn't based on forks. It was based on chopsticks, the initial version. And obviously, you need 2 chopsticks in order to be able to eat. But then the example was westernized, and now, for some reason, we need 2 forks in order to eat our lunch. So, since the forks are shared resources, we are going to have to use semaphores for representing each and every one of them. Now, the first and obviously wrong way of approaching this problem is to have the non-critical section where any of the philosophers, process I, thinks. Then it tries to acquire the left and right forks. So it's P2, in which case it will require F2 and F3. If it acquires them, both of them, in that case, he will eat. And afterwards, he or she will put the forks down. And of course, this can lead to a deadlock. Why? Because it is possible that each philosopher, each process will only execute successfully the first of the wait statements, meaning that each of the processes will only acquire the fork to its left. So each of the processes will only acquire 1 fork, nobody will have 2 forks, and they will starve and the system is locked. So the challenge is, how can you assure that a philosopher either gets two forks or no forks? Ya ikisini de alacak ya sadece ya da hiçbirini. Tabii sistem 5 ile bunu çözmek işten bile değil. Ama POSIX ile biraz saç yoldurtuyor insan. System 5, the easy part. Well, if you need two forks, that means you need two semaphores. All you have to do is just call a semop atomically with two semaphores. How can you do that? Now, first, you create the semaphores. How many? Well, equal to the number of forks. So IPC private, you don't care about the key. So we let the kernel associate the key with the semaphore set. This is a constant. 5 semaphores. We are telling it to create them. And we want an exclusive creation, just like with the creation of files. And here we have the permissions, octally combined. Once we have these forks, you can use semctl in order to initialize them. That part is missing, so you just simply give 1 to all of them. That's the initial value, the fork is available. And what happens if process I, int I, tries to get 2 forks? Well, in that case, we will need an operation on 2 semaphores. Well, that is why I have an array of 2 semboof ops. I have only 1 call to semop, but I'm using 2 operations atomically. Here I have the 2 operations. So an array of struct semboof. What is the index of the first semaphore? Well, it is the ith one. What is the index of the second operation? I plus 1, of course, modulo 5. And what am I supposed to do with these semaphores? Well, I am going to acquire them, so I have to lock them. So that means I will decrement their values, both of them, both the first one and the second one. So basically the ith one and the I plus first one. 2 wait operations. And the flags, well, the flags are set to 0. I don't care about the flags. That's a constant for now. And we simply call it semop. Here is the identity, the semaphore set identifier, forks. Here is the array containing the operations, struct semboof. And here is the length of that array. And that's it. So what is the result of this operation? So this means that when the ith process, or whoever calls it get fork with I, it will get to the semop system call, and it will either successfully complete both wait statements right here. So it will successfully decrement the value of both of those semaphores, the ith one and the I plus first one, or if it cannot do both of them, it will be blocked. But in no case will it acquire just one of them. So either 2 or nothing at all. And that's sufficient. And we have solved the Dynamic Philosopher's problem. Any questions about this? So what happens if you cannot use System 5 semaphores? Well, such baş olmaz zaman arkadaşlar. In general, when you cannot use, for some reason, System 5 semaphores, and you have to solve it with POSIX semaphores, you often need additional processes, additional semaphores, additional data structures, counters, and so on and so on. It gets unnecessarily complicated, but that is the price that we pay for portability. So the idea with the POSIX semaphores is simply that, yes, there can be a deadlock if there are 5 processes trying to acquire those forks, but if you limit them to only 4, then a deadlock is avoided, because if you have 4 processes, at least one of them will have the chance to get 2 forks, at least one. So you will avoid starvation. So what do? You use something that is called, which even has a name, as a multiplex pattern. So this is a concurrency pattern. We will talk about this in the, well, we will not talk about this in the design patterns course, because we will be focusing on other types of patterns. So this is a concurrency type of a pattern. And the idea is that we have an additional semaphore, in addition to the semaphores representing the forks, called the footman, that is initialized to 4. And his job, this footman's job, is to simply limit the active philosophers to 4 instead of 5, or whatever value you use for it as its initialization. So footman is initialized to 4. So if it is initialized to 4, and some process, the ith process, calls get forks I, if it succeeds in getting to the table, so wait footman, if it succeeds and gets to the second statement, it will get its left and right fork. If you have additional philosophers arriving in, so the second one, the third one, the fourth one, they will be able to get in. And of course, 3 of them will only get 1 fork, but 1 of them is guaranteed to get those 2 forks. Garanti. Eğer 5 tane çatal varsa, 4 tane de filozof varsa, bir tanesi tabii ki 2 tanesini alacak. And how did I guarantee that there are only 4 at the table actively? By using footnote. And of course, I operate symmetrically when they finish eating. So this is an example of the multiplex pattern. An additional semaphore limiting the number of processes actively operating upon the shared resources. Questions? The solution that you saw in the operating system course, was it similar to this? Something different? Hocam hiç hatırlamıyor. Sorma şu anda. Sistem kilit. Bilet kaydı ya. Burada mısınız gençler? Ne durumdasınız? Takip ediyor musunuz? Edemiyor musunuz? Biraz daha yavaş gidebiliriz. Efendim? Ediyorsunuz. Peki. İşletim sistemleri gördüğünüz örnek bu muydu? Başka bir örnek miydi? Busy waiting vardı. Yok canım o ölümcül bir günah olmaz o. O hayatta olmaz. Yusuf Hoca size busy waiting'de çözüm versin. Yok. Efendim? İkna etmişsiniz. Olur. Başımıza gökten taş yağacak arkadaşlar. Busy waiting görmeyin. Sakın bak. Sakın. Hani arada böyle yüklüyorsun uygulamayı. Çalıştırıyorsun. Bakıyorsun şöyle CPU böyle %100'e falan vuruyor. Başlıyor falan şöyle delirmeye. İşte o busy waiting. Yapmayın öyle şeyler. Müşteri hiç sevmiyor öyle şeyleri. Ben de sevmiyorum. Efendim? Aha, evet. Onu mu yaptınız? Tamam, güzel. Güzel arkadaşlar. Yazık, CPU'lara yazık. Yakında termal pastayı şöyle biraz daha gümüşlü bir şeyle değiştirsin. Okay, so this brings us to the next example. Not very politically correct, but this is the name that it is known by. The cigarette smokers from 1971, an old example. I wasn't born at the time. It has many variants. It has many variations. In one variations, for instance, we are not talking about cigarette smokers, we are talking about bakers that are trying to bake something. But the original example is with the cigarette smokers, and the idea is very simple. You have 4 processes involved, 4 processes. 3 of them are smokers. 3 of them are smokers. And these smokers, each of these smokers has an infinite supply of one of 3 ingredients. Now, each of these smokers wants to smoke. It's bad for their health, but they want to smoke. And in order to smoke, they need 3 ingredients: tobacco, paper, and matches. Each of the smokers has an infinite supply of one of these 3 ingredients. One of these 3 ingredients in a distinct fashion. So one smoker has an infinite supply of tobacco, the other one has an infinite supply of paper, and the third one has an infinite supply of matches. Which means each of them requires the other 2 ingredients. Okay, so they are infinitely waiting for the other 2 ingredients. And when those ingredients arrive, they take those 2 ingredients, they roll a cigarette, and they smoke. And the fourth process, who is a non-smoking agent, every once in a while, every few seconds, every few milliseconds, who knows, he arrives to the area where the smokers are and brings 2 random, distinct ingredients. So maybe he brings tobacco and matches, maybe he brings matches and paper, maybe he brings tobacco and paper. 2 ingredients, one of each, distinct. So normally, if you design this carefully, if it operates like a well-oiled machine, if the agent brings tobacco and paper, which smoker is going to be able to smoke? Well, if there's tobacco and paper, that means the smoker who has an infinite supply of matches will take those 2 ingredients. It will combine it with the third ingredient, Voltran'ı oluşturacak, tobacco, paper, and matches, roll a cigarette, and smoke. And the other 2 smokers, they will continue waiting, ideally. So this is what it looks like in general. So here we have the agent, every once in a while puts 2 ingredients on the table. He somehow signals to the smokers, all of them, that I have brought something, so wake up. And then he waits for the table to be cleared. So for somebody to come and take those ingredients. And when the table is cleared, he leaves, and after a while arrives again, returns with 2 more ingredients. And the smokers, they wait for the ingredients. If they are signaled that mallar geldi, they receive the signal, they take the ingredients, they signal back to the agent who was waiting. Ne bekliyordu? İşaret bekliyordu. Masa boşaldı mı? Aldınız mı malları diye. They signal back that the table is now empty so that the agent can leave in order to return with more ingredients. They smoke for a while, and the smokers then wait for the next round of ingredients. A first attempt, a lousy one. On the left, we have a smoker, the one that has an infinite supply of matches. And on the right, we have the agent. Now, the agent, very easy, an infinite loop. He is waiting for the table to clear, and then brings 2 random ingredients by posting the semaphores. So if he's posting paper and tobacco, that means he's signaling whoever is waiting for paper and or tobacco. And what about the smokers? Now, the one who has infinite matches needs tobacco and paper. So that smoker in an infinite loop is waiting for tobacco and paper. If both of these waits are successful, we'll get the ingredients, we'll smoke, and then it will post agent Sam to signal the agent that the table is now clear and we are done smoking, bring us more ingredients. And of course, this is obviously wrong. Why? What can go wrong? Buyurun. Yes, obviously. İsminiz neydi? Gökbey. Okay. Mr. Gökbey is right. Just like we saw in the previous examples, you have multiple smokers. So who else is waiting for tobacco or paper? So for instance, the smoker who has an infinite supply of paper, he needs matches and tobacco. So what happens if that smoker gets the tobacco first? Well, in that case, one smoker will get the tobacco, the other smoker will get the paper. Öyle bir şey olacak burada, olmayacak. One smoker can get the tobacco, and before having a chance to get the paper, some other smoker might get the paper because they are calling wait paper first. It's possible. It can happen. And during a demo, it will very probably happen. And what happens then? The smokers are deadlocked. They keep on waiting forever. The agent keeps on waiting for somebody to post agent Sam, but nobody is posting it because nobody can roll a cigarette. Sistem kilit. How do we solve this? Well, in order to solve this class, here for instance, we have the problem. So we have 2 smokers, one with matches, one with tobacco. So if one of them gets the tobacco and the other one gets the paper, well, the system is deadlocked. So this is very bad for the smokers, but good for their health. So how do you solve this with system 5 semaphores? Very easy, very easy. All you have to do is just use the atomic double wait on 2 semaphores. So either get both tobacco and paper or none of them. Bir tane semaphora bakıyor. Bitti. And that's it with system 5. Any questions about system 5? POSIX, you need 3 more processes in order to solve this, unfortunately. And you need quite a number more of semaphores. So this is here in order to show you the difference between the system 5 and POSIX semaphores when it comes to solving this type of issues. And it is a bit messy, so pay attention. We have 3 more processes. Zaten 4 tane vardı. Bir 3 tane daha geldi. Sadece senkronizasyonu çözmek için. Başka bir işleri yok. These are 3 helper processes called pushers in the state of the art, in the literature. And they respond to the signals from the agent and keep track of the available ingredients, signaling the appropriate smoker. So between the agent and the smokers, we now have an intermediate layer of pushers, helpers. And not only that, we have 3 flag variables, integers, booleans, is match, is tobacco, is paper. So these are 1 if that is the ingredient that is on the table. That is what they represent, these flags, the type of the ingredient on the table. And then we have 3 semaphores. 3 for the smokers, obviously, tobacco, paper, matches, but 3 more also for the pushers. Tobacco 2, paper 2, matches 2. Or, yeah, tam tersi aslına bakarsanız. Tobacco 2, paper 2, matches 2 for the smokers, and the original ones for the pushers. And of course, we have the additional semaphore for the agent. So we have 7 semaphores in total. Now, how are we supposed to use these? Now we will have 3 pushers, and what are these pushers doing? Now each pusher is waiting for one type of ingredient. Pusher A is waiting for tobacco. And what is it doing? Somebody is signaling it that there is tobacco. Who? The agent. The agent just brought, for instance, tobacco and paper. Post tobacco, pusher A wakes up, tries to get the lock. Why the lock? Because the table is a shared resource. There shouldn't be multiple processes accessing it simultaneously. If it can get the lock, it checks the table. Now, is the variable is paper set? Who is going to set that? The pushers. But this is the first pusher who is executing. There is no way that is paper is true. So it is false. Is paper, is match? No, it is also false. Else, well, in that case, set tobacco to true. Okay, he sets tobacco to true, which is normal. Why? Because he was woken up due to a post tobacco, so that there is definitely tobacco on that table, and then unlocks the table. Now the agent has brought 2 ingredients, tobacco and paper. So that means one more pusher will get to execute. The other pusher, pusher B will execute because there is paper. It will get the lock. It will check whether is tobacco is true, or it is true, because it was set right here. So is tobacco is set true. He's resetting it to false, resetting the system, and he's signaling who? The smoker. Which smoker? The one who is waiting for tobacco and paper. 2 aşamalı bir süreç arkadaşlar. 3 tane helper'ımız. We have 3 helpers. Each of them waiting for one type of ingredient. As soon as they see it, they are setting a flag, so the other pusher will see it. And the other pusher, as soon as he detects which flag has been set, he signals by posting the corresponding smoker. That's it. It's as simple as that. But we needed 3 additional processes, 3 additional semaphores, and 3 additional variables. The smokers, well, the smoker is very easy. They just wait for the signal from the pushers. Then they are certain that the table contains exactly the ingredients that they need. And of course, while getting the ingredients, they must lock and unlock the table inside get ingredients. Then they can smoke and finally signal the agent that he can now leave and bring new ingredients. Buyurun.
If we need more than 3 ingredients, for example, not just tobacco or something like that, we have 4 or 5 some different ingredients for smoking or something like that.
Mm-hmm.
So
let's say that we have, so for example, let's say that we need 5 ingredients.
Yes.
In order to make a cigarette.
Yes.
But you still have 3 smokers. Or do you have 5 smokers?
No. Just
Okay, now we have n smokers that also need those ingredients. Well, in that case, you will need, if you have n ingredients, you will need n pushers. 1 pusher per ingredient in order to make it work. And of course, you will have to also increase the corresponding number of semaphores.
we need more help.
Yes, more helper processes, more pusher processes. So n ingredients, n helpers. Acı var mı arkadaşlar? Hocam acı boş ver, uyku var diyorsunuz daha çok. Tamam. Yetişemeyin arkadaşlar. Bunların da ödevi geliyor. 1.34. Ara verelim mi? Tamam arkadaşlar, 10 dakika ara.